So I'm going to talk about climate change, air pollution, and public health impacts. I don't really know where the best place to stand is anymore, but I'll just and kind of take a view from the past all the way to the present and the future. So I want to start with just thinking about how have humans changed the composition of the Earth's air since pre-industrial times. This is a graph that many people are familiar with showing temperature change. I feel like I'm going to trip over here if I... showing temperature change from the 1880s to the present. You just think about the massive changes that have happened since humans really have been the dominating influence on the Earth's atmosphere. You consider when my grandma was born, the concentration of carbon dioxide in the air was 303 parts per million. About 30 years later, my parents were born 310 parts per million. I don't want to date myself too much, I didn't put the exact year on here, but in the early 1980s-ish, I was born, and the concentration of CO2 was 344 parts per million. My three kids then were born these years, and you can just see that the concentration of CO2 has been increasing not just steadily, but faster over time. You consider the fact that it took a whole generation between my grandma and my parents to go 7 parts per million. Here, just in the 4 years between my second kid and my third kid, we've had a 7 part per million rise. So the concentration of CO2 in the air has been increasing more rapidly. And this is not the only way that humans have influenced the air that we breathe. You think about air pollution as well. So about 90% of the world's population lives in areas where particulate matter, fine particulate matter, exceeds the World Health Organization guideline for PM 2.5. And that guideline is already too high. We know we have epidemiological and human studies evidence that shows that the health effects of air pollution are seen at lower and lower levels of pollution, indicating that this World Health Organization guideline is probably too high, and yet the vast majority of the world's population is breathing unclean air. Even in the United States, so the United States, we are, at a national scale, achieving this World Health Organization guideline. But there are lots of parts of the United States where people are breathing unclean air as well. This is kind of the quintessential graph that anyone who has ever worked at EPA, including myself, always shows in every talk. And this shows that air pollution has been declining over time since 1970, when the Clean Air Act was enacted. And this is actually the 50th anniversary of the Clean Air Act. It's been declining steadily over time, and even more so since the 1990s, when the Clean Air Act amendment was passed. So you can see that these aggregate emissions of fine particulate matter, or PM 2.5, ozone, nitrogen dioxide, sulfur dioxide, carbon monoxide, and lead have been declining. And this is a massive win in terms of the air that we're breathing. And this has happened while vehicle miles traveled have increased, gross domestic product has increased, population has increased, and CO2 emissions have increased. And that's really important, that there's been this diverging trend where air pollution emissions have gone down and CO2 emissions have gone up. You can actually see this efficacy of the Clean Air Act from space. So this is some maps developed by Brian Duncan from NASA, showing that nitrogen dioxide concentrations have declined by a massive amount from 2005 to 2016. This is viewed from the ozone monitoring instrument on a satellite. So we now have the capability of observing these massive human influences on air pollution from space. And this is really impactful on public health because there's quite an array of health outcomes that are associated with air pollution. We often talk about PM 2.5 mortality, but that's just the tip of the iceberg. There's a lot of different health outcomes that are associated with fine particulate matter, with ozone, with nitrogen dioxide. And the farther you get down this pyramid, the less severe the impact, but the broader array of the population that's impacted by these health outcomes. We know this evidence from systematic reviews done by the EPA, the Environmental Protection Agency, the World Health Organization, the EU, and others. And they make these causal determinations based on the epidemiological evidence and supported by the toxicological evidence. So this is just a kind of a snapshot of a few of the health outcomes that are causally associated or likely causally associated with air pollution, and there's additional ones here that I couldn't fit on this slide. There's really a broad array of health outcomes, and that actually the evidence is pointing to the fact that every organ is affected by air pollution. It's not just the respiratory system and cardiovascular system. This huge amount of air pollution has a huge amount of the health outcomes associated with air pollution, as well as the exposure, has placed air pollution as the number 5 leading risk factor on a global scale. So this is not the number 5 environmental health risk factor, this is the number 5 overall health risk factor for global populations. And you can see it's behind dietary risk, high blood pressure, but it's ahead of things like water, safety and health, low physical activity, and others. So this is really a large impact of air pollution on public health. And let's just talk about where air pollution comes from. So this is a really nice animation that some colleagues of mine at NASA have created, which shows how air pollution changes around the world. I love this because you could just zone out and watch this on the lava lamp for a while. But I think this really shows some important things. First of all, the air is dynamic. We are not exposed to one parcel of air in front of us. The air is constantly moving, constantly changing. We're all affecting each other. The emissions that we have in the United States travel across the Atlantic. The emissions from Africa are traveling over here. The emissions of South Africa are traveling over here. So we're all part of this global community that's breathing the same air. We're all breathing basically the same air. And you can see that the sources of air pollution are different depending on where you are. So you have both anthropogenic sources and you have natural sources. You can see, for example, this dust from the Sahara moving across the Atlantic. If you can also see these forest fires popping up here and here. If I talk long enough, you'll start to see the wildfires in Australia moving across the southern hemisphere as well. So it's important to consider, not just how do we address our anthropogenic emissions, but how does air pollution interact with the natural system? These are often considered natural sources of air pollution, wildfires and dust. We really need a better name for this because they're increasingly affected by anthropogenic climate change. So sometimes I talk about these geogenic air pollutants, things that are sort of affected by the natural system. Okay, so let's talk about how we take a more integrated view of this. You don't have to read all these words. I just want to point out that this is, the air quality and climate change are really integrated systems. You have emission sources, and these affect air quality and climate change. So anytime you're burning anything, you're releasing air pollution and climate change. Products of incomplete combustion is air pollution, and greenhouse gases like CO2. So you also have the impact of climate change on air quality. So climate change can affect air quality by affecting meteorology, photolysis rates, those geogenic or natural emissions that I talked about, like wildfire emissions and dust. And also anthropogenic emissions, more people using air conditioning, for example. That's an anthropogenic emission impact from climate change. Air quality also affects climate change. There are some air pollutants that also absorb incoming solar radiation or outgoing terrestrial radiation. Air pollution can affect the climate system by depositing on snow and ice-covered regions and reducing the planetary albedo or reflectivity. So there's different ways that air pollution can affect climate change, and of course both of these affect public health. So I'm going to talk first about how climate change affects air quality, then I'll talk about how we can mitigate both of these problems together. So about 10 years ago, when I was starting to learn about how climate change and air pollution interact, there was a new set of the papers that were coming out showing that there might be this climate penalty for ozone. So what that means is that holding all else the same, all anthropogenic emissions the same, we would anticipate that ozone would increase in the future just because of climate change. So climate change affects photolysis rates, it affects planetary meteorology, and so we can actually model how ozone concentrations would change under climate change. And this is the paper that sort of coined that term, that there's a climate penalty for ozone, and that view has somewhat persisted in the literature. And these are now model results from the National Climate Assessment. showing that under a lower scenario on the left, a lower climate change scenario on the left, and a higher climate change scenario on the right, and under 2050 at the top and 2090 at the bottom, we can model the increases in ozone concentrations as a result of climate change. You can see, large-scale increases of ozone throughout most of the Great Plains and Midwest. The literature has been more mixed, though, for PM 2.5. So, and that's because there's different conflicting ways that the climate change, that the climate system influences PM 2.5. So anytime you have increases in precipitation, rain is the main mechanism for removing particulate matter from the air. Anytime you have increases in precipitation or increases in atmospheric mixing, you would have PM 2.5 decreases. That would be a good thing for air quality. Anytime you have increased humidity, stagnation events, that's when air is kind of stagnant over one particular area, holding pollutants close to the ground. And natural emissions, those geogenic emissions, for example, PM 2.5 would increase. So this is some results that were published a few years ago from a study I wasn't involved in, showing how temperature increases PM 2.5 concentrations, relative humidity would decrease it, and precipitation would decrease it. But the results in the literature have been really mixed about the effect of climate change on fine particulate matter. And so we wanted to know, if we tried to zero in more on this natural emissions part of this, would we see that there's potentially climate penalty for PM 2.5 as well? Noticing that the mixed results in the literature are likely because each of these studies includes a different subset of these factors that affect PM 2.5 and not all of them together. So we're trying to increase our knowledge about these, the impact of climate change on these natural emissions. And the reason we wanted to understand better these natural emissions is because we have evidence that climate change is increasing wildfire frequency. And all you have to do is pay attention to California wildfires from last year to read all about this in the media, but it's also in the academic literature showing an increase in wildfire events throughout most ecoregions of the western U.S. Same for dust storms. So in the southwest U.S., we're seeing more dust storm frequency increasing as a result of climate change. So we wondered, if we're seeing more wildfires, we're seeing more dust storm events, we would expect there to be an increase in natural emissions of fine particulate matter. And so, what we try to answer is, we're looking at the future, right? We're looking at something that is unknowable, something that is untestable. All we can do is kind of project different scenarios of what we think might be plausible futures of the Earth. So here again is where my kids were born, and let's hope I'm lucky and I have grandkids one day. Here is the different possibilities of what the climate system might be doing in the United States. We could have this really high climate change scenario, which has, until very recently, been very considered as a business as usual scenario. We appear to be following this line. More recently, we're starting to see some evidence that just because of the drop in pricing of renewable energy, that this curve might actually be a little bit lower. So we're probably somewhere in between this sort of lower scenario and this higher scenario. We're definitely not on this even lower scenario. So we're somewhere around here. The good news is that we're not anticipating to be up here. The bad news is that being around here is really bad. So we still want to know, if we were to follow, one of these ranges of scenarios, or one of these scenarios in this range, what would be the effect of climate change on natural emissions? So we do this with, somehow this, one of these figures got dropped off, but that's okay. We do this type of work with our colleagues at the EPA who run a project called the Climate Change Impacts and Risk Analysis, or CIRA project. And the whole point of the CIRA project is to simulate the effects of climate change on all different sectors across the United States using a common set of inputs. A common set of scenarios, a common set of population scenarios, a common set of greenhouse gas scenarios, a common set of climate models, and a common set of analytical years. And by doing that, by using a common set of analytical inputs across all of these sectors, we can compare apples and apples across these sectors. We can see which sectors are expected to be more costly in terms of the damage from climate change. So you can see the current status is that these are the effects of climate change that have been quantified, and the effects on labor have been the most costly in terms of the effects that have been quantified. But followed by extreme temperature, mortality, then coastal property, and down here, the fourth position is air quality. That's pretty much just ozone, because that's the only thing, not pretty much just ozone, that is ozone, because that's been the only thing that's been quantified. So we want to know, is this circle too small because we're excluding the effects of these natural emissions of PM2.5? So we follow this common set of modeling inputs according to this EPA SIRA framework, and by doing so, again, we can compare apples with apples across these different sectors. And the general way we do this is we have emission scenarios, which I showed. There's a range of emission scenarios from really bad to pretty bad to somewhat bad. And then we have a range of climate models where we model the effect of those emission scenarios on temperature, on precipitation, and other meteorological variables. We then are able to take the climate model output, those meteorological variables, and use that as an input to an exposure model. That's an air pollution model, an atmospheric chemistry model that tells you, given temperature, precipitation, movement of air around the world, how do we anticipate ozone and fine particulate matter to respond? We then have health impact functions that are based on epidemiological literature, and then health damages. We can turn this into a dollar value based on valuation techniques like value of statistical life, cost of illness approaches. So some important considerations when doing here, you can see that this is a complex set of modeling tools that we have to bring together to address these kinds of problems. And as you can imagine, there's uncertainties along the way here, at every step along the way. So some things that we do to try to mitigate those uncertainties. Number one, we have multiple future climate scenarios. So we acknowledge we can never predict the future, right? We're not in the business of predicting here. We're just simulating what could happen under different plausible futures. The second thing is that we use multi-model ensembles of multiple climate models. So there's an old saying that says all models are bad, but some are useful. We kind of apply that here. Models are only as good as our representation of atmospheric processes in those models. So we don't know which one is right, which one is better. So we just try to use multiple models to try to, get sort of a range of responses that are plausible. We also look at decadal eras to account for interannual variability. So there's some natural variability that just happens year to year, right? And that's not due to climate change, that just happens. So to try to tease out the effect of climate change, we average over sometimes a 10-year period, sometimes a 20-year period, and that way we can try to remove the influence of interannual variability. And then finally, there's different models. I'm using sort of simple terms here, but there's statistical models, there's process-based models. Statistical models would say, given a historical set of meteorological observations and wildfire area burned, we can correlate the two, and let's assume that the links, the associations between those two hold in the future. Then we can project what happens under climate change in terms of the climate influence on wildfire area burned. That type of approach is useful in many ways. One thing it's not useful for is telling us why the association is there and which factors of climate change would be driving that relationship. So that's why we also have process-based exposure models. These are built upon our understanding of the natural system. And so we can develop models based on how climate change influences drought conditions or evapotranspiration, and these types of influences on atmospheric conditions and on natural emissions like wildfires. They're both useful in a way and not useful in another way. The way that process-based exposure models are not useful is that what if our understanding of the way the world system works is wrong? It's only as good as our representation in these essentially a set of equations that become a model. So these are some considerations for how we can increase the confidence in our results. Okay, so moving on to some of the results of this type of analysis that we've done with the EPA and their climate change and impacts and risk analysis program. they wanted to know, they have already estimated the impacts of climate change on ozone and ozone-related mortality. They wanted to know how much will dust change, how much will dust concentrations in the air change under climate change. So we employ this modeling framework and we ask ourselves, how will dust levels change due to projected future drought conditions in the Southwest US? And so we bring a multi-model ensemble. Each X here represents a different model's realization. The black line is the average, and then over there, RCP 4.5 is sort of the moderate climate change scenario. RCP 8.5 is severe climate change. And we see that under both of these scenarios, every single model predicts an increase in dust concentrations in the air of the Southwest US. In fact, projected decreases in soil moisture could increase fine dust levels by 57% over the US Southwest in 2090 under this severe climate change scenario. And that we predicted larger impacts under RCP 8.5, the severe climate change, versus RCP 4.5, the more moderate climate change. We can, as I mentioned, use epidemiological relationships to turn this into a health impact. And what we found is that in 2090, dust attributable mortality could increase by 220% due to the combination of rises in dust, population, and baseline disease rates. And if we just try to pull out the climate portion of this, we find that climate-driven changes in dust concentrations alone account for about 40% of this increase. And this was some work published by my former postdoc, Ploy Ajakalwasit, last year. So, my thinking prior to this was that, this is probably not going to be a huge impact of climate change. We're just talking about the Southwest US here. We're just talking about dust, which is really a small part of overall air pollution. But what we found is that the $47 billion per year cost of these health impacts was about twice as large as the ozone impact, and dust then became the fourth highest impact of climate change. And again, we can do this because we followed the same modeling scenario, the same modeling inputs, the same climate scenarios, the same climate models, the same population scenarios, and so we can compare across all these different sectors, and we find that dust is number 4. So that was pretty significant. That was kind of, in fact, it blew me away how big that impact was, and that's going to go into the National Climate Assessment now. So next we wanted to know about wildfire smoke. How much will wildfire smoke increase in the future, and what will be the health impact of that increase in wildfire smoke? So what we're looking at now is this purple circle here, which which I've added to this figure. We don't know what is the impact of wildfire smoke on human health under climate change. And yet we think that this is going to be pretty significant because you can actually see wildfire smoke from space. It is, when wildfires occur, the smoke really, really changes air quality. It really worsens air quality. So that was the California fires from last year, and then you can see down here that there's the smoke from those wildfires doesn't just stay in the area, it travels all the way across the United States and even around the world. And so it's not just the California population that is affected by these wildfires, it's us here in DC that are also affected. It's everyone around the world. So when you consider that the wildfires are becoming more frequent, and there's a huge global population that's exposed to this increase in wildfires, you would anticipate this to be quite a significant impact. So we just tested this with one model just to see how big the impact would be. So what you have here on the left is the fire-related PM 2.5 in the year 2000, and then 2050 here, 2100 on the right. RCP 4.5, again, moderate scenario on the top and a more severe scenario on the bottom. And you can see, everywhere we're anticipating based on this one model simulation, we're anticipating that wildfire PM 2.5 will increase into the future. When you apply the epidemiological relationships to this increase in wildfire PM, you see that this is the graph of total PM 2.5 mortality in the United States. By the time you get out here to 2100, we anticipate this decline in overall PM 2.5 related mortality due to the decline from anthropogenic emissions, which is not really guaranteed anymore based on who is running the EPA right now and who will potentially be running the EPA for the next 4 years. But if you assume that this anthropogenic decline persists and continues, then this total magnitude of the PM 2.5 related bar goes down. And then you see a larger fraction of the bar becomes from fire-related PM 2.5. This kind of peachish transport portion is transported fire-related PM 2.5 from Canada and Mexico. So what this indicates is that fire-related PM2.5 could actually dominate PM2.5 mortality in the United States in the future. This really shows quite a striking figure about how important this problem could become, at least when you look at a more severe climate change scenario. But what this analysis did is, and this was published in GeoHealth last year, I think it was last year. Anyway, what it did is that it only used one model. It did not use the same set of climate scenarios, the same set of climate models used by the EPA Sierra program. And so that's what we're doing next, is to be able to compare apples and apples across these different sectors. We're now using those different climate scenarios that everyone else is using. And we're using the same climate models that everyone else is using. And these are the early results of that project, is that we see increases in black carbon and organic carbon emissions coming from wildfires under both the moderate and severe climate scenario. We model that through to PM2.5 impacts and mortality. And what we found is that PM2.5 mortality from wildfire emissions increases from $6 billion per year to $40 billion per year in 2090 for the more moderate scenario, and $47 billion under the more severe climate change scenario. But this jumbles together climate change, population, baseline disease rate changes. So the next step is that we have to pull out just the climate change impact from this. So right now this is work in progress. It's not a conclusion yet. But what this is pointing to is that the impact of wildfire is actually much smaller than I anticipated it could be. Again, that could be because of our modeling setup. So we have some work to do to kind of tease that out. But what this is kind of starting to show me is that the dust impact might be larger than we thought. The wildfire impact may be smaller than we thought. I don't know. So, stay tuned. So what I've kind of come to focus on now is that we have seen this precipitous decline in U.S. Air pollution emissions, and yet at the same time we have this increase in CO2 emissions. So if these CO2 emissions are driving a potential climate penalty both for ozone and for PM2.5, we may not see this decline continue in the future because of climate change. Even if we were to continue to decline our anthropogenic emissions of these pollutants, just the CO2 increase may be making that more challenging and may actually increase pollution in the future. So I started thinking about the hierarchy of hazard control that's often used in occupational settings. If you think about PPE, personal protective equipment, that would be like walking around in a face mask to try to protect yourself from exposure to air pollution. What we have been doing is engineering controls, kind of a moderate level of this hierarchy of hazard control. We've been basically, this decline has occurred because all of our cars now have catalytic converters and diesel particulate filters, and we have scrubbers on our power plants that take the pollutants out of the emission stream. But we're continuing to burn the same amount of stuff. We're continuing to burn coal, we're continuing to burn gasoline, natural gas, and we're not taking the CO2 emissions out of that emission stream. And so we see CO2 emissions increase while aggregate emissions of air pollutants have been decreasing. What we really want to do is eliminate the hazard, right? We want to eliminate the CO2 emissions and the air pollutant emissions to solve both of these problems simultaneously. So if you look at this interconnected system graph that I showed before, what we've been doing is focusing there. We've been taking air pollutants out of effluent streams. What we need to be doing is focusing here by reducing emissions in the first place. So that has led me to a focus on cities more recently. Cities are the source of about 70% of the world's CO2 emissions. They're also highly polluted. This is a map made by research scientist Dan Goldberg, who's sitting out there. And you can see that both CO2 emissions and nitrogen dioxide observed from satellites are really highly concentrated in urban areas. So this is the source of CO2 emissions, the source of pollution. And also many of these cities, as shown in the red bars here, also have increasing air pollution levels. Most cities around the world are expected to increase in terms of air pollution. We also have a massive urbanization happening. So about half the world's population lives in urban areas now, and about 2/3 of the world's population is expected to live in urban areas by 2050. And massive inequality problems. So here is a map of DC with asthma prevalence, and you see much higher rates in this part of the city than in that part of the city. So you have some, health challenges happening, some inequality challenges happening within these urban areas. So when you think about the cost of climate change and the focus on cities, the academic literature has been making this point for a long time, that cities can reap local and immediate health benefits from taking action on climate change, but it hasn't really made its way into practice. And I would guess that that's partly because for cities taking action on greenhouse gases, the whole world benefits over the long term, over centuries, but it's that city that is bearing the cost. So why would that city, let's say Washington, D.C., undertake the cost of mitigating greenhouse gases when the climate benefits of those reduced greenhouse gases would be felt only globally and over centuries, and yet the cost is felt really locally? If you flip that consideration and think about the local air quality and health benefits that would come from reducing greenhouse gas emissions, all of a sudden now you have this massive local and immediate health benefit that can be compared against the local and immediate cost. The problem is, and I think this is potentially one reason that this has not gone from the academic literature into practice yet, is that cities around the world don't know what their air pollution levels are or the health benefits of reducing air pollution levels. In fact, this is a map of PM 2.5 monitors per million people. And you can see that much of the world has zero monitors. And in much of the rest of the world, they might have one monitor within like a huge area. This is not enough to tell people what air pollution levels are in cities worldwide. And in fact, this map comes from a paper titled something like "Nobody Knows What the Most Polluted City on Earth Is." And I think that's a really good descriptive title because, basically this picture is, it's a picture of the lack of information, right? We don't have the public health surveillance that we need for cities to take that information and make decisions on it. What we do have now, though, is recent advances in satellite remote sensing and chemical transport modeling, in using proxies to fill in the gaps where we have no monitors. And this is the same research group that produces this map now, using a combination of satellite data, chemical transport modeling, and other sources. And we do now have gridded estimates of air pollution levels all around the world. So we can take this information and generate information for cities to be able to get a sense for, may not be as accurate as having, a monitoring network locally, but we have some information about what global air pollution levels are. So what we want to do is try to take this out of the academic literature and provide information that can be used by cities to get a sense for what the air pollution levels are and what would be the health benefits of taking action to address greenhouse gases. So I'm just going to show you a snapshot of a few efforts that we've done just in the last year to try to generate that kind of information. This was a paper we published a few months ago in Scientific Reports that shows PM 2.5 mortality around the world. And we found that PM 2.5 mortality ranged tenfold from the best performing cities to the least performing cities within the most populated 250 cities worldwide. So there's a huge range in how cities are doing here. And what was also really interesting was that PM 2.5 mortality did not necessarily follow PM 2.5 concentrations. So the most polluted cities were not necessarily the cities that were most vulnerable to the health impacts of air pollution. We also generated a new method to estimate the health impacts of nitrogen dioxide pollution. It's a major component of traffic-related emissions, largely in urban areas. And what we were able to find is that the percent of total pediatric asthma incidence in each city that was attributable to nitrogen dioxide ranged up to 50%, and that was in Shanghai. So what that means is that half of pediatric asthma incidents, half of new cases of asthma in Shanghai were attributable to traffic-related NO2 pollution, nitrogen dioxide pollution. these are preventable cases of asthma. These are occurring because of the traffic-related air pollution. It was not just Shanghai. You can see Shanghai is not existing in isolation in terms of a high bar here. Almost every one of these top, I think in this study was 125 cities, the fraction of total pediatric asthma incidence that was from NO2 was above 20%. We can also estimate the sources of emissions and their impact on PM2.5 and ozone-related mortality. So this was some work that we did with International Council on Clean Transportation. It was published a few months ago in Environmental Research Letters. And can you see the map here? Yeah. Okay, so the red colors here show the portion of air pollution-related mortality in each city that are attributable to transportation tailpipe emissions. And you can see the reddest colors are in Europe and Mexico City. And that basically indicates that these are places that have addressed their other sources of air pollution. You get the largest impacts, though, in terms of the overall magnitude of transportation tailpipe emissions in these Asian cities. So by starting to zero in on the sources of air pollution, we make this more policy relevant. We can give information to cities that says, if you were to address your transportation tailpipe emissions, here are the health benefits that you would get to your local population. And this is some new work that is kind of ongoing. These are plots that were developed by Dan Goldberg out there and Veronica Sutherland right there, showing how air pollution levels have changed over time in these cities. And so what we're going to do next is try to figure out, for cities that have signed on to something like the C40's network of cities gearing towards zero carbon emissions, or the Climate and Clean Air Coalition, some of these large city networks, do those cities perform better than other cities that have not signed on to these city networks? What's the effect of that kind of decision making? And what I've shown so far is just comparing cities around the world. It's not showing what's happening within the cities. And that we know that there's a lot of spatial heterogeneity and health inequality problems that's occurring within cities. So this was some work done by Alex Lindahl, a former GEH student, for 4 US cities and 4 health outcomes that are affected by air pollution to see what's the spatial pattern of health impacts of air pollution happening within these cities at the census block level. And just looking at DC at the bottom here, you can see large impacts of PM2.5 on asthma in the southeast, but the impacts on COPD, lung cancer, and stroke are higher in the northeast. Part of this, I think, is driven by age structure. There's older populations in northeast. But I think that the point is still made here that is largely it's not just driven by the total pollutant levels, it's also driven by the health status of the population that's breathing in those pollution levels. And this is some preliminary work from Veronica Sutherland as well, where we've partnered with Environmental Defense Fund. EDF has itself partnered with Google to measure air pollution on Google Street View mapping cars throughout the Bay Area and Houston. So they literally are driving around these Google Street View mapping cars with air pollution sensors on them, measuring air pollution at the street level. And we can use that information that shows the variation of pollution levels across the city. We can use that information to see who among these, these neighborhoods within these populations is most affected by air pollution, most vulnerable to the health impacts of air pollution. And as you can see, there's quite a bit of spatial variability happening here. And that indicates that we can't just have one number for the whole population, for the whole city, right? We have to understand what's going on at a neighborhood level. So, globally, cities are experiencing poor air quality, poor health, health inequality, and high greenhouse gas emissions. If only there was some way we could solve these problems. If only. And the thing is, we do know, we've had this information, that we can solve these problems through sustainability planning. So the way we've been reducing air pollution is through, again, these technological engineering controls that we've input on our cars and our power plants. We have diesel particulate filters and catalytic converters and scrubbers. We've largely taken these air pollutants out of effluent streams, but we haven't done anything for CO2 emissions. The only way to solve both of these problems is to burn less stuff in the first place. So, burn less coal, burn less gas, burn less natural gas. And we can do this through sustainability planning, things like active transportation, zero emission energy, and energy efficiency, as evidenced by our building that we're in right now. And if you were to implement these measures here, you would not just reduce greenhouse gases, you would also reduce air pollutants. And you would improve health in many ways beyond just the reduction in air pollution by increasing physical activity, improving mental health by having greater access to green space. There's a number of win-win-wins happening here through sustainability planning. And so our next step, these are two projects that we have undergoing, we're working on right now. Both of these actually recently started, where we're trying to make that bridge from the academic literature to the end users now. So recognizing that, again, this academic body of literature has been existing for a long time, showing that there are these local and immediate health benefits of climate action planning, but they're not being considered when cities are undertaking climate action planning. So we're working directly with the end users from the Climate Clean Air Coalition, Stockholm Environment Institute, and in this project, C40 Cities, which is undertaking the largest urban climate action planning worldwide, undergoing right now. And in both of these there are two different projects using two different sets of techniques, but in both of them, the commonality is that we're developing sort of reduced form air quality models that can be integrated into the tools that these groups are already using for climate action planning. And we're reducing the complexity, the need for cities to undertake their own chemical transport modeling and their own very resource-intensive and expensive and time-consuming analyses. We're doing that ahead of time and boiling it down to more simplistic relationships and integrating it into the software that they're using with their cities right now, and giving cities access to information about the air quality improvements and the public health benefits for different types of mitigation measures that they can undertake. So that will be happening over the next year or two. So just some key takeaways: that air pollution continues to be a massive global health risk factor, even in the United States and other countries that have largely addressed the air pollution problems. We're seeing health impacts of air pollution levels even at present concentrations in the United States. Climate change may exacerbate these air pollution levels, and so in the future it's important not just to consider how do we reduce air pollution using these engineering end of pipe controls, but rather move towards elimination, move towards reducing burning of all different kinds of stuff in the first place. And those urban actions that would reduce burning would yield local and immediate health benefits that would be additional to the centuries-long and global-scale climate benefits. Now, the key question is, will this health impact information that we're making available to cities, will it actually influence urban decision-making? And this is fodder for research for the next 5 to 10 years. So, thank you very much.